Okay, so remember what we're talking about? Matrix representations, linear transformations. Right. You have, again, say it again. Right. You have some linear transformation from one vector space to another vector space. Right. And you create this thing that goes from Rn to Rm. So V is some n-dimensional space, and W is some m-dimensional space. Yeah. Right. You've got some n-dimensional space, you've got some m-dimensional space, and you create this map, you create a matrix that goes from Rn to Rm, and somehow this matrix encapsulates everything that T does, right? It does what T does, it reflects it. It's like a mirror of it. Okay, so it's an exact duplicate of it in its own parallel universe. Okay. I've been watching The Flash on Netflix.
Season 2?
What?
Are you on season 2 then?
I've already passed season 2.
Okay.
Okay. So right. Parallel universe, right? different world, but they do exactly the same things. Okay. Right, and in the sense that if we take a vector over here and map it over here, we take V to TV, or we take these representate the coordinate vector of V with respect to E, and map it to TAVE, that's the same thing as AVE, right? That's AVE. Then these things are related to each other, right? This TV and AVE, right? V corresponds to VE. TV corresponds to AVE, in the sense that this is the coordinate vector of this, and this is the coordinate vector of this, right? This is the coordinate vector of this, right? This is the coordinate vector of this. Okay. Okay. So this is exactly what's going on when we say we have a matrix representation. Okay. So I just to make one thing clear, right? We could, if we went, basically, remember these guys can go backwards, right? These maps are isomorphisms, so they can go backwards. Okay, right? What we call P and Q. Actually, there's a P inverse and a Q inverse, right? Because these are one-to-one Opti maps, right? So they can go backwards. The point of this picture is that if we go down like this and then come back up, we get TV, right? Or if we go across, we get TV, right? Or if we start here and we go up and down, basically it doesn't matter what paths we take. As long as we start and end at the same place, we're going to get the same thing. Okay. So this diagram, right? You can. It's better. It really commutes, right? You could go this way and this way. You could go this way and this way. You could go this way and this way, this way and this way. As long as you start and end at the same place, you get the same thing. Okay. So yeah. Okay. So that's the point of creating this matrix representation. This is really the same thing as this, just in its own Euclidean world, as opposed to this abstract vector space world. Okay. So today we're going to do something called similarity. What we're going to do is we're going to look at the relation between matrix representations of the same operator, the same linear transformation, but with respect to different bases. With respect to different bases. Okay, so we need one term that linear operator is just a linear transformation. Okay, it's a linear transformation from the same, from and to the same vector space. From and to the same vector space. Okay, so it's a linear, just, I mean, if you just think of it as a linear transformation, it's a linear transformation. Okay, so yeah, put your phone away, please. Put your phone away. Okay, so what we're going to be having is something like this. We have a linear transformation going from one vector space back to itself. Okay, and you have a single basis. So let B be a basis of B. And we'll use the basis on both sides. We'll use the same basis on both sides. And we'll get a matrix representation with respect to the B basis on both sides. So maybe I'll write B color B. Okay, so this is just a simpler version of what we're doing over here. Okay, it's a simpler version of what we're doing over here. The difference is that we don't have W. We're just going to use V on both sides. We don't have different bases. We don't have E and F. We have E and E, right? We have the same basis. We have the same basis on both sides. Okay, and you take the matrix representation. Take the matrix representation of T with respect to those two bases, B and B. I'm just going to write B because it's why do I need two matrices? Okay, makes sense? Right. You get the right? So notice if I change B to a different basis, then I get a different matrix representation, right? AB prime. Right? We get a different matrix representation. AB prime. And our question is, the question that we're going to talk about today, the question we're going to answer today is, what's the relation between AB and AB prime? What's the relation between AB and AB prime? Okay. Does anybody know the relation? Has anybody read ahead, maybe? Or even if you haven't read ahead, can you imagine what the relation might be? Let me draw a picture. So we've got our transformation going from V to V, right? We've got one matrix representation, AB, right? We also have our second, so we've got one basis here, but we've also got another basis for B that we can use on both sides to get a different matrix representation, right? We can get a different matrix representation for AB. What's the relationship between this guy and this guy? Okay. Montana?
Would it just be multiplied by a transition matrix?
Yes. So Montana actually figured this out before this class ever happened. Like at the end of last class, Montana, or 2 classes ago, Montana came up and said, blah, 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 blah. I was like, oh, you get fucked. No, how many points? Anyway, I forget if I gave you any points, but you definitely deserve at least 3 or 4 on the next exam. So what's the relation between AB and AB prime, right? The thing is this, that in this picture, going across here is the same thing as going like this, right? Because these guys are the matrix representations, right? If I go up here and down, that's the same thing as going here and down, but that's the same as going across like this. Okay, so these diagrams, anyway, the thing is that going all the way around is the same thing as going across. Okay, so that tells you that multiplying something by AB is the same thing as taking the vector. So if you have your vector here and multiply it by AB, it's the same thing as going all the way over here, hitting that guy with AB prime, and then coming back down. Okay, so you just have to figure out what's going on from here to here. Okay, now think of what this does. This map here takes your vector B and brings it to the coordinate vector with respect to B. Right? This map here takes your vector B and maps it to the coordinate vector with respect to B prime. Right? Well, that means that this map here is the map, right? This map here is the map taking the coordinate vector with respect to B to the coordinate vector with respect to B prime, right? That we've seen before, right? That's accomplished by multiplying by the transition matrix, right? This is affected by multiplying by the transition matrix from B to B prime. Right? Right? Do you remember how we get the transition matrix? It was kind of funny. You had to take your basis elements, express them in terms of the other basis elements, and then take the transpose of the coefficients. Remember that? Everyone remember that? Right? You take these guys, express them in terms of these guys, and then you transpose those coefficients, and you get this matrix. Right? That was the transition matrix. Okay. So in any case, what this picture is saying is that if you start from here and go across, it's the same thing as starting here and multiplying by the transition matrix from B to B prime, then multiplying by AB prime, and then multiplying by the inverse of the transition matrix from B to B prime. Right? Of course, that's the same thing as the transition matrix from B prime to B. Right? Yeah, Connor.
S is the transition matrix.
Yeah, S is the transition matrix. So I'm using this notation. The transition matrix going from B to B prime. The inverse of the transition matrix from B to B prime. But that's the same as the transition matrix from B prime to B. You could write it either way, but I'm going to write it this way. Okay.
How do you multiply it twice by the transition matrix?
Well, because I have to get back, right? Right. I want to go up and across and then down again, right? Going up, across, and down is the same thing as going across, right? So I have to multiply. I have to multiply first by. I first go from B to B prime, then multiply by the B prime matrix, and then use the B prime inverse matrix to get back home again. Okay. Everybody sort of getting it? Yeah, check.
I was wondering if you could go in the other direction, so that's
Yeah. Yeah, absolutely. Yeah. So you see that you could say that AB prime is the same thing as going this way across and back. Is that what you're saying?
Yes.
Yeah. So you could say I'm going to take SBB prime inverse first, follow that with AB, and then come back to SBB prime. Right? That's the same thing.
Why did you write it backwards instead of, like, why did you start from there, go in?
That's how you write a composition. Like if I'm saying if I write f of x is sine x and g of x is x squared, then f composed with g, the g happens first, right? The g happens first and then the f. Right? This is f of g of x. Right? So same thing here. Right? The first thing, if I'm for this one say, if I'm first doing this, then I put this one first. Right? Like this thing is going to happen. This thing is going to act on the vector. This thing is going to act on that thing, and then this thing is going to act on that thing. Okay. It's just the composition notation. Yeah. When you have linear transformations, then, well, this is how you write them. Okay, so, yeah, Mariah.
Wait, why don't those matrices cancel? If S being the inverse.
I mean, if they were next to each other, yeah, they would cancel, right? But they're not next to each other.
Yeah.
Right, because you can't, we don't have commutative property. Right, so. Okay. Yeah, okay. So I hope everybody's getting the point here that the relationship between the two matrix representations is that you can get from one to the other by multiplying by the inverse on one side and the matrix on the other side by some transition matrix. Okay, this process, we call this conjugation. Okay, that is, you can get to from one guy to the other via conjugation. Okay, one guy is the conjugate of the other, and vice versa, right? This guy is the conjugate of that guy, right? This guy is the conjugate of that guy. This guy is the conjugate of that guy. Yeah, if you're conjugates, that's a mutual relation. Okay, so let me write that up more formally. I'm just going to write the same thing, but as a theorem. So if T, so theorem if T from B to B is a linear operator, and E is a basis of B, and F a basis of B. Then if S sub EF is the transition matrix from E to F, right, taking coordinate vector with respect to E to the coordinate vector with respect to F, then the matrix representation, right, the matrix representation of T with respect to the E basis equals SEF AF SEF inverse. Yeah, Jen.
For the second arrow, which says matrix representation with respect to F and F, is that F and F basis?
Yeah.
Wait, sorry, why is F and why isn't it with respect to F?
If you want to say with respect to F, that's fine. I'm just saying F and F because we're using it on both sides. Like when you take a matrix representation, you've got a basis on one side and you've got a basis on the other side. But we're using the same basis. We're using the same. When we say A sub B, we mean using the same basis on both sides.
I thought we had different bases on each F.
So don't get confused. It's okay. It's okay to get confused because there's a lot going on, but try not to get confused. We have two bases. You've got one basis and you've got another basis. Okay. We use one of the bases to get a matrix representation with respect to that same basis on both sides. We use the other basis to get a matrix representation with respect to that basis on that other basis on both sides. And what we're saying is that those two representations are related. Okay, so we're not taking one basis here and then a different basis here. We're not taking different bases, right? And then, I don't know, taking some more bases up here. Okay, we're not doing something like that. We could, but it wouldn't be so pretty. Okay. Right, we're doing something simpler. Okay. So let me make this concrete with an example. So let's go back to something we've seen before. Differentiation on P3. Okay. So we've got P3, we've got the derivative going between them. Okay, and just as we had before, let B denote 1x squared. Okay, then if we use that basis on both sides, right? If we use the basis on both sides, we can get a matrix representation with respect to those two identical bases, right? You can get the matrix representation with respect to these bases, right? 1x squared. Take half a minute and do it, just to remind yourself how to do it. And reassure yourselves that this is something that you've seen before.
Sorry, how do you differentiate and stay in P3?
Well, it's still in P3, right?
Okay.
Technically.
Yeah. Okay.
Right. I mean, you could say it's in P2, but I don't want to say that. Okay, so how do you get it? Somebody tell me. Anybody remember? Tana, how about you? No? Sally, how about you? Nope. Mariah?
And you just like differentiate the bases.
And then?
And then you express it as linear function of the bases.
Yeah, yeah. Say, right, so A sub B, you're going to get, the columns are going to be, you take D of 1 with respect to the B basis, D of x with respect to the B basis, D of x squared with respect to the B basis. Okay? You take the elements of your basis, you transform them, and then you represent them with respect to the second basis, but the second basis is the same as the first basis. Right? And you see what you get, right? It's going to be 0, 0, 0, because the derivative of 1 is 0, which is expressed as 0 of this plus 0 of that plus 0 of that. Then you get 1, which is 1, 0, 0, right? And then you get 2x. That's going to be 2, 0, 2, 0. Okay? Everybody okay? Did we remember?
Why is it 0, 2, 0?
0, 2, 0, because when you differentiate x squared, you get 2x, right? And then you express it as a linear combination of these guys. Well, it's 0, 0, and 2 of these elements. Okay. Okay. Now, let's take our second basis, v, as 1, 2x, 4x squared minus 2. Okay, and we can get, as we just did, we can get a matrix representation with respect to the V basis. Okay, so maybe do that just for practice again. Okay. Turn to somebody nearby and say, this is what I got. Okay, what did people get? 0, 0, 0, 2, 0, 0, 0, 4, 0. Okay, everybody all right with that? Right, 0, 0, 0, 2, 0, 0. Yeah, right, because, right, the derivative of 1, the derivative of 2x, and the derivative of 4x squared minus 2 are 0, 2, and 8x, which, if you express them with respect to the b basis, are 0, 0, 0, right, 2, 0, 0, and 8x is 4 2x's, right? 8x is 4 2x's. Right. Okay. Okay. And so what we've been saying here is that these guys are related to each other, right? That we can get one from the other using a transition matrix. So the theorem says that AVV equals SVB AVB SVB inverse. Right? So we can check it. So just for practice, let's recall, how do we get SVB? Well, you take each element of V, right? And you express them in terms of the B basis, right? So this is going to be 1 plus 0 plus 0. This is going to be 0 plus 2 plus 0. This is going to be negative 2 plus 0 plus 4. Right? Express V in terms of B. And then you transpose the coefficients. And you get that SVB is 1, 0, 0, 0, 2, 0, negative 2, 0, 4.
So if we were to find SB1, SBB prime instead of this, like the inverse, would it be better to try and represent that as a linear combination of the other instead of trying to find the inverse of this matrix? There's two transition matrices there, right?
Yeah.
Instead of trying to invert this, wouldn't it be easier to just do the same thing?
Good. Yeah. Yeah. That'd be fine, because that will be the inverse matrix. Yeah. Yeah. Okay. And then you just check. I leave it to you to see that this in fact works out. That when you take so S inverse turns out to be 1, 0, half, 1, 0, half, 0, half, 0, 0, 0, quarter. You can check that this times this times this equals this guy. So it's easy to see this, right? So easy to see that the matrix with respect to B is the same thing. If you multiply it by this and this, you get this. So, in some sense, you can see that you wouldn't necessarily want to find find these guys in this way, right? It's actually easier to find them directly, right? If you want to find ABV or ABB, then do I have it backwards? I have it backwards. Well, anyway, this is true. Yeah, maybe.
Yeah. So that's.
So I'll just write. So it's easy to see that ABV is SBB followed by ABB followed by SBB. But like I was just saying, this isn't the easiest way to get ABV, right? As you see, it's just easier to do it directly. It may be easier to do it directly. But the point is that right? What's the point of all this? The point is that matrix representations of the same linear operators with respect to different bases are related. Okay. Now, I actually don't want to say related. The mathematical word is what we call similar. Okay. So let me give the definition of similar. We say the matrices A and B are similar if there exists an invertible S such that B equals S inverse AS. Okay, or we say that B is a conjugate of A. Okay. Yeah, Mariah.
Only works if the linear operator goes, your stays in the same vector space.
Yeah. I mean, you can do it if it doesn't, but it would just be a little bit trickier. It'll be trickier. Okay. So, yeah, Connor.
So the thing you erased is wrong, you said?
The word related?
No, the thing you erased, the matrices that we had read out.
I think I'd written the wrong matrix or something like that.
No,
The matrix was right, you just labeled them wrong.
Oh, okay, I see. I labeled them wrong. Sorry. Okay. So what's the point? The point is that if you have the matrix if you have different matrix representations of the same linear operator, then the matrices are similar to each other. The matrices are conjugates of each other. notice that of course, if A is similar to B, then B is similar to A, right? A is similar to B, if only if B is similar to A. Okay, so, right, so point matrix representations of the same linear operator are similar, right? I'm not going to write it again. Same linear operator are similar. There's also a converse statement, which is also true. If A is a matrix representation of T, then S inverse AS is also a matrix representation of T. S inverse AS is also a matrix representation of T. Okay. I'm going to leave that as an exercise. You don't have to edit it, but you should think. You might want to think about it. Okay. Anyway, so the point at this point is that every linear transformation is going to correspond to a bunch of matrices, all of which are similar to each other. Okay, right? Each linear operator corresponds to what's called an equivalence class of matrices, all similar to each other. Okay, and so it's in our interest to find the simplest one, right? My 7th grade math teacher always used the word behooves. It behooves us to find the simplest one. Okay. Do we have time to do the example? I'm not sure. Let's see. Let's start. Well, I'm wasting time talking about my 7th grade math teacher. We all admired him, and we all wanted to be like him. Okay, so L, the operator, let L be the operator on P3, given by L of P of x equals x P prime x plus P prime x. Okay, so right, you've got this operator. What it does is it takes a polynomial, differentiates it, multiplies it by x, and adds on the derivative to it. Right. So if we fed it like x squared, right, you would say, okay, I'm going to take the derivative, multiply by that, and I'm going to add on the derivative. Right. So we get 2x squared plus 2x. Okay, that's what it would do. Okay. So if you made a matrix representation of this with respect to the standard 1x squared basis, r cubed to r cubed, you'd find out, so I'm going to rush it a little bit, you'd find out it would look like this: 0, 0, 2, 0, 1, 0, 0, 0, 2. So suppose I say, I want you to, the question is, what is L100 of 3x plus 5 plus 5x squared? So I want you to take this thing and apply the operator to it 100 times. Go. Right? It's awful, right? You have to differentiate this, multiply it by x, and add on the derivative, then do that again, then do that again, do that 100 times. Okay? You could do it. It'd be awful. Right? Or you could use the matrix representation. That's a little bit better, right? Because you would say, okay, I take my 5 plus 3x plus 5x squared, I take its coordinate vector. What's the coordinate vector? 5, 3, 5. And I multiply it by this matrix 100 times. Right? I multiply it by this matrix 100 times, and then I map it backwards, back up. Right? That's easier than I think than actually doing it in your brain, right? With your brain. Right? So you could do it that way. But there's something even better. Let v be 1x, 1 plus x squared. Okay. Sorry, since we're running over time, I'm just going to just do it for you. The matrix representation ABV, right? So this guy here was our ABV. The matrix representation ABV turns out to be, well, maybe you can see it, right? If we take one, differentiate it, multiply it by x, and add on the derivative, we get 0, right? So L of 1 is 0, L of x turns out to be x again, L of 1 plus x squared turns out to be 2, 1 plus x squared. And so the matrix turns out to be 0, 0, 0, 0, 1, 0, 0, 0, 2. Okay, which is great, right? Because what's great about this? You say, okay, so if you have this guy 3x plus 5 plus 5x squared, what does that get mapped to in the v basis? Well, that'll be 0, 3, 5. Right? 0, 3, 5. Right? Okay. And then you just need to multiply that by this matrix multiplied by itself 100 times. Right? But it's a diagonal matrix. So multiplying it by itself 100 times is easy. Right? You just get 0, 0, 0, 0, 1, 0, 0, 0, 2 to the 100. Right? 0, 3, 5. And so we end up with 0, 3, 5 times 2 to the 100. Right? And so that corresponds up here to 3x plus 5 times 2 to the 100 times 1 plus x squared. Right? And so that's the answer. Okay, I think I went through this too quickly. What?
over there,
Yeah.
you did L of 1 is 0, and then L of x equals to x.
Yeah.
So if we're doing that, L shouldn't be x times P of x, which is 1 plus 1.
P prime is 1, x plus 1. Oh, yeah, that's right.
So even there, even over there, the matrix should be the second
Oh,
column.
I'm sorry. This should be the second derivative.
Oh.
I'm really sorry.
Sorry, what's
Yeah,
going
yeah.
on?
Sorry. Yeah, sorry, I messed up.
That makes more sense.
Sorry. Yeah.
That makes more sense.
Okay, maybe I'll do this again at the beginning. That was a bit too fast. But anyway, the point is that this is a lot easier. If you change the basis, it becomes a lot easier. So I'll do it again next time.
Will we be sending like the list of topics like that?
Yes, I just haven't had time to